That's what I'm hearing.
Hello and welcome back to Calculus 3, section 16.7 on change of variables in multiple integration. So, what we have is technically U-substitution on steroids. Let's talk about Calculus 1 U-substitution first. So, Calc 1. Integral of x e to the x squared dx. One of the cool problems for U sub. The way to integrate this is to transform the integral from x domain into u domain by creating a transformation function u equals x squared. So we are replacing domain x with a completely new domain u. This is known as transformation when you are changing the space, technically. Your quadratic space of x squared changed into a linear space, u, right? Then we take the derivative that gives us this differential du equals 2x dx. And then we plug these values into the integral. Now I don't have this u, this 2, so I'm going to fix that real quick. There we go. And now my integral becomes 1/2 integral of e to the u du. Now, if I had limits which went from x1 to x2, because those were the x values, a and b, on x-axis, those limits would have to be converted such that I get u1 to be x1 squared and u2 to be x2 squared. So you are using, use transformation function to come up with limits. And then these limits become u1 and u2. What I have done here is I transformed the space that was with the domain x into a completely new integral, which is in terms of variable u, and variable u becomes independent variable, and the entire integral is now in a different actually space. Now, when you take a look at the graphs of the two integrals, they have nothing to do with each other. But what's cool is that they produce the same answer. You have seen this before with L'Hopital's rule in Calc 1. When you have 0 over 0 or infinity over infinity, and you L'Hopital rule, you take the derivatives, right, independent derivatives of numerator and denominator, you get completely different functions. The two expressions have nothing to do with each other than being linked through these independent derivatives, but they have the same outcome. They have the same answer. So in some sense, this would be the same thing. The integral on top and the integral on the bottom have nothing to do with each other if you are to graph the function, because x e to the x squared doesn't look anything like e to the x, right? They're completely different functions. But the answer that they produce is the same answer, so we are allowed and able to do the U-substitution, and we are able to, through the transformation, actually compute the values. So that's our calculus. That's our calculus 1 calculation. Now, when we integrate this, we get 1/2 e to the u from u1 to u2, and then you actually compute the number, and you're done. So I really hope that you are all familiar with calculus 1 procedure. Now, one thing that most of the students actually don't know is this, which is transforming the limits. Unfortunately, most of the instruction in mathematics happens this way. Just integrate and then go back to x and plug in all limits. Yes, you can do it that way. It's a little bit longer, right? But the issue is that you never learned that you are supposed to transform the domain as well, right? Not just a variable changes x to u, but your limits have to also change from x to u, and you don't have to go back to x to compute limits if you did the transformation for those limits. Well, that was something that you could cut corners with in Calc 1 U-Sub, but you can't cut corners in Calc 3 now. You have to transform the region first. And those regions are not this. They are two-dimensional regions or three-dimensional regions, which you have to transform through transformations given, and the transformation given is actually your U-Sub formula. Now we're going to have a u and v, and then UVW, right, for triple integrals. So it's going to be much more work than this. As it goes, let's go, work it out. We need to make sure that our wrists don't fall off. Each problem is 40 minutes, so let's go. We are going into Calc 3. The first order of business is to learn to transform the region. So transformations in a plane or transformations in 3D, depending on what type of integral you have. So change of variables in double integral is a transformation that relates two sets of variables uv and xy. Your problem is given as the variable of xy. It works on cats.
Yeah.
Your problem is given in x and y. You are transforming the region into uv. So we need to have a transformation. So your transformation will be given like this. Transformation of x equals g of uv and y equals h of uv. So we are going to change our variables from one domain into another domain. So now let's take a look at the process, because we need to see this monster at work. So let's go and transform a region. So I'll work out the one that is done in the book, and then we'll work one from the homework. So you have two examples. It's not as easy and trivial to follow it. So let's go. So transformation is given as x equals g of r theta to be r cosine theta. And y is h of r theta, which is the conversion from y into r sine theta. Guys, this is just your basic formulas that are converting polar into rectangular coordinates. So now you are given region S, and region S is equal to all points r theta such that 0 is less equal than r, less equal than 1, and 0 is less equal than theta, less equal than pi over 2. So this is your region. Now, I want to transform. Now, this region that it's given to you over here is actually a rectangle. And then when we do the transformation, it will turn into what you actually want it to be, which is a quarter of a circle. So I have a region like this, and this is in r theta realm that goes from 0 to 1 and 0 to pi over 2. And if you notice over here, you have 4 lines, right? You have 4 different regions. I'll label those, well, the book labels them A, B, C, D, so I'm going to use the same. I usually put 1, 2, 3, 4, but here, A, B, C, and D. So all of these are our lines. So now, what I need to do is to write the formula for each one of these. Guys, this is a standard procedure. This is how your problems start, right? So now you write for part A, this formula that the formula that you have is what? R is stuck between 0 and 1, while theta is equal to 0. Do we all see that? You see how R goes from 0 to 1 and theta is exactly 0? B should help. For B, R is equal to 1 all the time, and theta is stuck between what? 0 and pi over 2. Good. For region C, R is stuck between 0 and 1. Theta is equal to pi over 2 at all times. And for region D, which is the last line we consider over here, the R is always 0, and theta is stuck between 0 and pi over 2. So now that you have all 4 functions listed, just try to make sure and sort out this in your head to see the way that I mathematically described each one of the 4 parts of the rectangle. Are we green here? Good. It is time to use my transformation and create XY equivalent of this. My transformation is given by x equals r cosine theta and y equals r sine theta. And I will graph what I get now in the xy plane, because I am transforming region S into this new region, which would be on xy plane. We can call this now A prime, which is the image of A. So what do I get? Well, I have to get 2 different equations, one for x and one for y, using this as input in these equations. Great. So if I have equation x equals r cosine theta, and I have my theta always equal to 0, I am always considering r cosine of 0 which is always just r. So my transformation is x equals r, but transformation x equals r, and r is stuck between 0 and 1. That just means that x is stuck between 0 and 1. Did this make any sense? Let me go through this one more time just in case. Because theta is always 0. There is no recipe for this. You have to think. Because theta is always 0, theta will always be 0, cosine of 0 will always be 1, so it's r times 1 equals r. So we are getting that x is equal to r. Because x is equal to r, and r is stuck between 0 and 1, that immediately means that x is stuck between 0 and 1. I need to do the same thing for y. Y function is r sine theta. Well, if it's r sine theta, and theta is always 0, this is r sine 0, which is r times 0, which means y is always 0. So I have my two new equations, and I'll use blue for this now. So I'll change this into blue, 0 less than x less than 1, and y equals 0 is the first line. That's my a prime, and I get to draw that now. X is stuck between 0 and 1. So here we go. On the elevation y equals 0. So this is my a prime between 0 and 1. I'm going to use a prime and the black one over here. There we go. So I have transformed a. Transformation for b is going to be called b prime. The whole argument starts from scratch. R is fixed to b1. So immediately my x is equal to cosine theta, and my y is equal to sine theta. Immediately, right? Because r is 1. Now, what happens as your x is equal to cosine theta? Well, I hope you guys see that r being 1 and theta being from 0 to 2 pi, it's going to swipe a quarter circle from x-axis to y-axis. So x equals cosine theta, and y equals sine theta is the set of parametric equations for circle of radius 1. And that circle is that theta goes from 0 to pi over 2. So this circle here now is going to be the quarter circle, because we have to end at pi over 2. X equal cosine theta, y equal sine theta is the unit circle if it goes from 0 to 2 pi. But it goes only to pi over 2, so we have to chop it up at pi over 2. So this is your transformation for b prime. C prime, your r is between 0 and 1, and the theta is always pi over 2. Well, if theta is always pi over 2, then your cosine of pi over 2 is equal to 0, and your sine of pi over 2 is equal to 1. So the x is equal to r times 0, which is 0, so x is always 0. And y equals r times 1, so y is equal to r. Well, that means that y is stuck between 0 and 1 because r was stuck between 0 and 1. Now that gives us this one over here, and that's your C prime. So I'm going to call this x equals 0, blue equation, we graph, and 0 less equal than y less equal than 1. All of these were supposed to be blue. Whatever. D prime, I have r equal to 0, and when r is equal to 0, that just kills both of these. So you have your x equals 0 times cosine theta, well that's 0, and y equals 0 times sine theta, that's also 0, so x equals 0, y equals 0 gives you a point 0, 0 at the origin. So origin only, single point is your D prime. So this problem transformed, one problem over here, transformed the region, the rectangle, into a quarter circle using the polar coordinates. Now, looking at this transformation and knowing what you know for polar coordinates, what do I have to change on the black graph so that I get half a circle? Yes?
Increase theta.
Increase theta to pi. Yeah, to pi, right? If you want 3/4 of a circle, shoot it up to 3 pi over 2. If you want the full circle, go all the way to 2 pi, right? So what you have seen here is a procedure to transform rectangle into a quarter circle. That's the transformation we have. Let's see if we can get a different transformation. We'll pick something from homework with the U and V and stuff. So here it is. Transformations, okay. Problem 8. Transformation that is given to us is x equals 2u plus v. This is the ones that you will be staring at all the time. And y equals 2u. That's the transformation. We are transforming S, which is region that it's given to us as 0 less than u less than 1. Oh, this is a square. 0 less than v. I shouldn't have said that. I should have asked you. I'm a terrible person. Thank you. It means a lot to me. 1, 1, 1, 1, 0, 0. And these are uv. I want to transform this into x, y domain. So, first order of business, is to A, B, C, D, write 4 regions. So I'm going to let you try writing those regions. Give you 2.5 minutes. Go.
Are you still on Hello.
Oh,
Is that watch me? Is that watch me or something?
Yes.
That's a 4 hour video.
All right, so A, we see that our U is stuck between 0 and 1, and V is always 0. B, our U is always 1, V is stuck between 0 and 1. C, our U is stuck between 0 and 1, our V is always 1, and finally our U is always 0, and V is stuck between 0 and 1. Great. Now we are going to transform this region using the formulas given in transformation. So I need A prime, B prime, C prime, and D prime. So what do I have? I have a V is equal to 0. If V is equal to 0, well, I have that X is equal to 2U. X is equal to 2U. And if X is equal to 2U, then, and U goes from 0 to 1, then X must go from what to what? Think. If X is equal to 2U,
0 to 1
so is it 0 to 1/2 or 0 to 2? So this is what you have to think about and write down the correct answer. So it's either a half or it's a 2. And when you start thinking and then you start panicking, right? So calm yourself down. Think twice and 3 times. Is it going to be 0 to 2 or 0 to a half? And whatever you pick, why? There is a very easy way to compute exactly, but I just want to make a point that it's very easy to make a mistake if you just rush through these things. So let's learn the trick. If you don't want to think and break your head, guys, look at this. It's really cute. U equals x over 2. Right? So you plug that in the equation 0 less than x over 2 less than 1. And to get x out, you multiply the entire triple inequality by 2 to kill the denominator, and I'm going to erase all this. And you get that your x is in between 0 and 2. Y is also 2u, so 0 less than x, less than 2 as well for y. So we have our A prime. Transformation for B prime. U is always 1. So if U is always 1, then we have x equals 2 plus v, and y is equal to 2, always. Well, that's already an equation. And I have that x is equal to 2 plus v. So v is equal to x minus 2. And when you plug that into 0 less equal than v, which is x minus 2, less equal than 1, and then you add 2 to each one of these, you get the second equation, which is 2 less equal than x less equal than 3, and y equal to 2. I'll point with blue arrows to the rows that contain equations we have to graph. C prime transformation. For C prime transformation, v is always 1. So since v is always 1, I have x equals 2u plus 1 and y equals to 2u. That's where we start. Now, when you calculate your u from here, your u is equal to x minus 1 over 2. And that's what goes between 0 and 1. Multiply the whole thing by 2. You get 0 less than x minus 1 less than 2. And then add 1 everywhere to get 1 less equal than x less equal than 3. Rinse and repeat for y. U is equal to y over 2, and u is between 0 and 1. So now you have times 2 to give you 0 less than y less than 2. So these are the two that you have to graph. And finally d prime u is always 0. Since u is always 0, then my transformation is x equals v and y equals 0 all the time. Where did I plug u equals 0? I plug that here, right, in the transformation. So when u is equal to 0, it kills this term, it kills this as well, so y is always 0 and x is equal to v. So v is between 0 and 1, so x equals v between 0 and 1. So the two equations that we worry about is 0 less than x less than 1 and y equals 0. Those are the two that we have to graph. Okay, let's graph. So now I don't have any negative numbers. I'm just going to ignore the negatives. And my x, my y. I am going to use 2 units. All right, let's 1, 2, 3. 1 and 2. Let's see what we get. So region A prime, x is 0 to 2, and y is 0 to 2. Now, what would that be? How about we do the other ones and then we come back to that? Let's do B prime then. So what's the B prime? B prime is y is always 2, and then we go from 2 to 3. All right, so B prime was easy. At least that. C prime, we have 1 less than x less than 3 and 0. Holy nightmare, that's another bad one. So let's skip that one. We don't know what it is, right? Let's go to D. D prime, whew, that's easy. Y equals 0, 0 to 1. That's this. That's D prime. So, can you tell me now what A prime would be? What's the A prime? It is that one. And the other one is this. So that's your A prime, and that's your C prime. So we transform the region. Now, what actually is going to happen in problems, you are supposed to transform from the shape like this back into the square for easy integration. I will cross that bridge when we get there. So these transformation problems, the substitution problems we are covering in 16.7, they have 3 parts. Part number 1 is to transform region. Part number 2 is to do the differential, and then part number 3 is to actually integrate. So this is the way to transform regions. You have to draw the region. You have to come up with A, B, C, how many of these lines you have, and then you will transform each one of them using the transformation. And the transformation is actually your substitution that you will be using later for the rest. So that's part 1 of the problem that we are facing. Transforming regions. Part 2, maybe I should call them part 1, part 2, part 3. I think I use red for part 2, compute Jacobian. Because you also need that transformation with, remember how you had the differential part, that the du equals blah, 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 dx? Well, part of that is in this Jacobian. Now, we don't do the proof for this. Jacobian of uv for 2D is a 2 by 2 matrix. It's a determinant of 2 by 2 matrix, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. And then you compute the determinant, which is partial x, partial u, partial y, partial v, minus partial y, partial u, partial x, partial v. Sometimes this will be a number, sometimes it's going to be a function. And this is the part that transforms your So now let me go back to Calculus 1 example of U-sub and tell you that transforming regions corresponds to this part. Transformation that it's usually given to you in Calc 3 is this part, and this is your Jacobian over here. But you only had one variable, so you did not have to go through all of these crazy calculations. So your region transformation, your Jacobian, and the transformation itself, which is your U-sub. So your U-sub has all of the features of what we are doing now, except now you're in multidimensional calculus, so you have to spend more time and figure out way more things. So now we know how to compute Jacobian. And finally, part 3, substitution formula. You transformed the region, you found the Jacobian, you can finally compile the two-dimensional change of variables. So substitution formula 2D, you can also put R2, whatever you like better. And here it is. The double integral over the region R for f of xy dA. Whatever that integral was, transforms into the new region S, where your function f is x is given as a function of GUV, y is given as a function age uv, all of this times the Jacobian uv, and then you have a dA. Now, I'm going to first box this because this is your 2D formula, and then I'm going to use blue to tell you that this dA is dx dy or dy dx, whatever is more convenient, and this dA on this side is du dv or dv du, again, depending on what's more convenient. So your xy integral becomes uv integral. We transformed the region, so region is now uv. We did the Jacobian, which is the equivalent to doing the du dv thing. And then we also transformed the function from x and y to u and v. So those are all three components that we need for our calculation. We'll take a look at the 3D later. We are going to do a full problem now to see all of the components necessary to solve this. Yes?
So when we were just integrating normally, we would kind of just tell that we would need U-sub, like when we were trying to solve an integral. Is there any way, like from a two-dimensional like integral like this, that we can just sit there and look at it and say, oh, we're going to need to do a 2D U-sub or a multiple variable substitution?
No. And especially not in this time when you don't have, a month to learn this.
All right, so the problem, like if we get a problem like this, it's just going to be do the multiple variable.
Yeah, it's going to be do this.
Okay.
Because you really don't have time to sit and each problem. We're going to do a full problem now, so mark the time we start, and just keep in mind that I've been doing this for years, so for me this is a flow. Right? When you start doing this, it's going to take more time, right? So that's let's go and see the full problem from transforming the region all the way into Jacobian, all the way into this. So we are starting now, which is 8:45, well, 8:43. Well, it will be 4:44 p.m. by the time I write this stuff. So let's go with whatever problem. Say 28 is fine. Double integral over the region R of x squared y dA, where your region R is given as x, y points such that 0 is stuck, x is stuck between 0 and 2, and y is stuck between x and x plus 4. And they tell us the transformation. So use the transformation x equals 2u and y equals 4v plus 2u. When this is not given, it introduces the entire new level of headache to figure out what is the transformation to use. Right? That's another step. All right, so now my first order of business, so we are starting the problem. So we are actually starting at 45. Okay, so 45. We are starting a problem now. I'm going to draw the region. And the region that I have is xy, and I will be changing that region into uv region. So I have a region xy. My x is in between 0 and 2. Okay, that's fine. The y, this equation over here has two equations that I need to graph. One equation is y equals x, and the other equation is y equals x plus 4. So y equals x is a 45-degree line, and then y equals x plus 4, 1, 2, 3, 4, is another 45-degree line. Now, my x is stuck between 0 and 2. So this is the region. This is the region R. For this region R, I have 4 parts that I need to transform into. So now I have to figure out what A is. Now if you take a look at A, that's the function y equals x. And x is between 0 and 1. For region B, your x is always equal. No, x is between 0 and 2, sorry. For region B, x is always 2, and your y is stuck between 2 and 6, right? Because we have these numbers, 1, 2, 3, 4, 5, and 6, and this is 1 and this is 2. Region C is our y equals x plus 4 function, and x is stuck between 0 and 2. And region D is x is always equal to 0, and y is stuck between 0 and 4. So now I need to transform all of these into u's, but if you take a look carefully at the transformation is backwards, right? Transformation is x equals and y equals. It's not u equals and v equals. So now I have to do an entire piece of calculation just to flip that on the side. Well, let's do that orange. Flip. I need, so u is going to be x over 2. That's what I need. And I need to plug that into the other to get the other transformation. So now I have that y is equal to 4v plus 2 times, and u is x over 2. So we will calculate v from here. 2's cancel. So y is equal to 4v plus x, from where 4v is equal to y minus x, and finally v equals to y minus x over 4. So my transformation that I have to use to transform the red stuff is actually u equals x over 2 and v equals y minus x over 4. That's the transformation that I have to use. So let's go with a prime. I have to transform the regions. I don't know the limits for my double integral if I don't transform the region and draw the picture for it. I must transform the region, and then I know the limits for the double integral. So a prime, y is equal to x. Okay, y is equal to x. So do we all agree y equals to x gives us a 0 here? Because y minus x then will be 0. So we immediately see that v is going to be 0 all the time. And if y is equal to x, right, then u is going to be, well, we know that x is equal to 2u, so you will have 0, 2u, 2, so u will be from 0 to 1. Yay, we got that one. B prime, x is equal to 2. So if x is equal to 2, that means that the 2u is equal to 2, so u is 1. And in the second equation, what do we have for the v? If u is equal to 1, y is equal to, so u equals to 1, y equals 4v plus 2. and y goes from 2 to 6. Y goes from 2 to 6, so this is 2 less equal than 4v plus 2 less than 6. Divide everywhere by 2. No, subtract 2 everywhere, sorry. Subtract 2 everywhere. 0 less than 4v less than 4. Divide by 4, 0 less than v less than 1. Holy nightmare, there we go. C prime. For C, we have y is x plus 4. And x is between 0 and 2. Y is equal to 2u. No, x is equal to 2u. Y is equal to x plus 4. And 0 less than x less than 2. Great. So we know that this one over here is going to quickly give us x was 2u. So that's 0 less than u less than 1, the same like we had above, and that's done. And now for this equation here on y is equal to x plus 4, so if you take a look at your transformation, you can move x to the other side. Y minus x is equal to 4, and you have the transformation v equals y minus x over 4. So when you replace y minus x with 4, you get that v is equal to 4 over 4, and you get 1. Great. And finally, d prime. D prime is going to be given as, what do I have up there? X equals 0 and y 0 to 4. So x equals 0, that means u is equal to 0. Great. And the y is given as 4v plus 0. So v is between 0 and 1. Yay, we got this. That's a transformation. So now we draw the picture. Now this is going to be our uv realm. A prime, v equals to 0, and u 0 to 1. So let's say this is where 1 is. So this is your A prime. And then B prime, your U is always 1. And you go 0. U is 1 and V is, so U is equal to 1 and V is 0 to 1. So you get this one. V equals 1, U equals 0 to 1. That's this one for C prime. And finally for D, U equals 0 and V 0 to 1. Oh, that's D. Sorry, I graphed this wrong. So A, B, C, D. We got a square. So instead of integrating over that parallelogram R, we did the transformation and we got the new space, which is a square. Much more, right? Much easier to integrate over. Well, there's no free lunch. The next part is to figure out our Jacobian UV. And Jacobian UV, so partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. We have the formula which says x equals 2u and y equals 4v plus 2u. So all you need to do is to fill this in. So it's equal to partial derivative of x in respect to u is 2. Partial derivative of x in respect to v is 0. Partial derivative of y in respect to u is 2. Partial derivative of y in respect to v is 4. To find the determinant over here, right, we go this way. So 2 times 4 minus 0, so that's 8 minus 0 equals to 8. So our Jacobian this time is just a number, 8. I can finally set up the integral. So now this is the final stretch over here. We have double integral. Hey, it's 0 to 1, 0 to 1. It's a square, right? That's easy. And now I have to transform the integral, which was given as x squared y. So x squared y needs to be written in terms of u's and v's. So x is 2u, so that's going to be 2u squared. And then y is 4v plus 2u. All of that times Jacobian 8. And then we have finally du dv. So 2 squared is 4 times 8 is 32 in front of the double integral. And then I have 4u squared v plus 2u cubed du dv. We can actually kick 2 out as well. So that's going to give me a 2 over here and makes this into a 64. All right, there we go. And all we need to do is to integrate this now. So 64 integral 0 to 1, integrate in respect to u. That's going to be 2u cubed v over 3 plus u to the 4 over 4 from 0 to 1. Still have dv to deal with. This is when I plug in 1 for u, we'll have 64 integral 0 to 1. It's going to be 2v over 3 plus 1/4 dv, which is going to give us 64, open parenthesis, v squared over 3, the half will cancel the 2, plus 1/4 v, computed from 0 to 1. This is equal to 64 times 1/3 plus 1/4, right? And then zeros kill everything. And this is 64, that's 7 over 12. So 64 times 7 over 12. And we cancel by 4. So that's going to be 16 times 7 over 3. Good to go. And the problem is done. And that's not, so it took 15 minutes.
15 minutes, 13 seconds on the clock.
Well, thank you for it. So here, 9 p.m. So it took 15 minutes, and I know what I'm doing because I've been doing this for years. Now, the first problem, right, you try on your own, it's probably going to take like 40 minutes or something, because it takes.
If there's anything on the quizzes in the try.
There should be.
Oh.
Yay. But you said the problems you give us are like supposed to be 5 minutes each.
Well, that was a lie, obviously, for this test. I believe that the exam will probably have like 8 questions this time, because each one of these integrals, right? You're calculating triple integral. what I said yesterday in class, guys, if you missed, and you did, if you missed the centroid stuff, right?
She's not here today.
When I showed the equations for the triple, the 3D, right? You have the mass, you have 3 moments. They're all triple integrals, right? It's very systematic on which way you memorize these, because they all have density function and then x, y, z, which is the only one that's missing in their moments over there. Joke to remember this. But how many integrals you have in one problem? 12 Calc 1 integrals, right? Because each triple integral is 3 Calculus 1 integrations, right? To go out times 4. So I said you're going to have either the double symmetry or a double integral with a single symmetry, so you don't have to calculate 15,000 integrals, right? It's one problem with a triple integral that it has no symmetry. It can take 40, 50 minutes. You calculate in 12 integrals and setting up 12 integrals. So all of these sections are very, very messy, and change of variables. Is it hard? Did we do any space stuff? Nuclear physics? Or no rocket science there. 90% of this stuff is basic algebra. But it's so long and so messy and that it takes time. Let's do another one. Why not?
I think of a lot of things. Why not?
Oh, I want to go home. No. No one is going home. We did problem 28. Okay. Problem 30. Do you get to integrate inside the ellipse? Do you? The answer to that is hell no. Well, this integral is going to have an ellipse. So that means that the smart transformation should transform that very hostile integral in elliptical space in something that it's manageable to do. So they want a very simple xy dA, right? This one, if you have a double integral with xy with limits, you should be able to mentally solve that problem without writing anything down. The issue is that the region R is given as the ellipse 9x squared plus 4y squared equals 36. And this is why you just cry, right? Because you can't do the limits. So now, we're going to use the transformation x equals 2u and y equals 3v. Now, I hope you immediately see what happens here. Does anyone see what happens if I use this transformation? If you plug these, if you replace values, we don't have to go now and do the entire region, because you may just plug these into this equation here, because we only have one line. Just plug them in. So I get 9 times 2u squared plus 4 times 3v squared equals 36. Do you all see 36u squared plus 36v squared is equal to 36? Cancels to what? Which is? Holy nightmare, that saves the day, right? That really saves the day. So we immediately got our transformation from the x domain into a uv domain, and a uv domain is the unit circle radius 1. And that's a joke to integrate. Obviously, if you change into polar coordinates. If you don't change to polar coordinates, then it's still nightmare because you have to do trig sub, right? But you're smarter than that. So we're done with transformation. We moved from the ellipse into a circle. Now it's time to do the Jacobian. Partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Hello, Jacobian, right? Partial x, partial u is 2. Partial x, partial v is 0. Partial y, partial u is 0. Partial y, partial v is 3. Jacobian is 6. Double integral of xy dA is going to be double integral, and now I have my x is equal to 2u, v is equal to, y is equal to 3v, times Jacobian 6 du dv. And over here, I'm just going to say circle r equal 1. Because I am not working in these rectangular coordinates for a circle. 2 times 3 times 6, that's a 36. Double integral uv du dv. Change into polar. Right? And then go from there. So to change into polar, we have 36, double integral. We have to transform. So these are your new x and a y. So that's r cosine theta times r sine theta, right? So r cosine theta, r sine theta. So this puppy over here is your u, and this puppy over here is your v. And you have the string r dr d theta. Your r is from 0 to 1, and your theta is from 0 to 2 pi. And problem is solved. 36, double integral 0, 0, 2 pi and 1. R cubed cosine theta sine theta dr d theta. Integrate r cubed to get 36, 0 to 2 pi r4 over 4 from 0 to 1. Still have cosine theta sine theta d theta to deal with. When you plug in 1, you get a quarter. That knocks 36 down into a 9. And all I need to do is the Calc1 integral cosine theta sine theta d theta. And now, what is the fast way to compute this integral? Let me see your Calc1 mad skills. I said cool way, not the brute force. I understand this, U-sub, yes. Anyone? What's sine theta times cosine theta in the identity? No. I said we want to do this the boss way. Sine theta times cosine theta is 1/2 of sine 2 theta. So this becomes 9/2 integral of sine 2 theta, because that one we don't have to use U-sub to solve. I said boss way, right? So 9/2 sine 2 theta integral of sine is a negative cosine 2 theta over 2, computed from 0 to 2 pi. So that's negative 9 over 2, negative 9 over 4, sorry. And then we have cosine of what do we have here? I can't think anymore. I'm so done. Cosine of 4 pi, right? And minus gives us plus cosine of 0. They need to be negative. I'm getting a negative integral. Getting a negative number is getting a positive number. I messed something up somewhere. Welcome to 16.7. Such is life, man. Right? You sign up for Calc 3 and then that's what you get. You get Calc 3, right? Just this. It's not hard, it's just annoying as hell. Yeah. Well, that's even worse. Now you get 0. Something is wrong. Wrong. I don't know. It's somewhere over here. It's wrong somewhere over here. Because we transform this into a unit circle and then we your u and v are a new x and a y, and then you transform all of those into polar coordinates. So your u is x, so it should be cosine, yep, r cosine, and then v is y, which is r sine, good. And then string for the polar, r dr d theta, that's 3r, so r cubed times cosine times sine. 36 doesn't matter, it's just coefficient. So r to 4 is 4, you get the cosine there. Sine 2 theta, integral of sine is a negative cosine. Negative goes to 9 over 4 cosine. And you plug 2 pi. I am overseeing something over here because we are getting 0 and I don't like it. Cosine of 4 pi is 1, cosine of 0 is 1, 1 minus 1 is 0, negative 9 quarters times 0 is going to be 0. Now, if I didn't use my fancy formula, but use the U sub, as you suggested, then we would have a sine, of we would have a U equals sine for the U sub, then a cosine. So we would integrate that one, we would get U squared over 2, so you get your 9/2. Now you have sine squared over, well, it's just sine squared, and when you calculate, oh, well, you still get 0. So this is probably right then. You still get 0, even if you do U sub, you get 0, and if you do it this way, you get 0. So we'll accept the answer, accept the fate. I remember first time I got kicked out of class, math class in school, I posed a philosophical question. Why did we waste all this time if the answer at the end is nothing? Get out. All right. Well, that was cool, right? That was cool. Let's take a break, and we'll talk about the exam when we come back.
I see.